Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Designing SoCs for USB Type-C Products, brought to you by Synopsys, Tech Online, and broadcast by UBM. I'm Chris Keachin. I'll be your moderator today. We have just a few brief announcements before we begin. First, you can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. At this time, we recommend you disable your computer's pop-up blockers. The slides will advance automatically throughout the event, and you may also download a copy of the slides by clicking on the Additional Resources button located below the presentation window. Also, if you're experiencing any technical problems, please visit our webinar help guide by clicking on the Help link below the presentation window. In addition, you can contact our technical support helpline, which is also located in the webinar help guide. And now on to the presentation, Designing SoCs for USB Type-C Products. Discussing today's topic is Morten Christensen. Morten is the Technical Marketing Manager for Synopsys' DesignWare USB IP. Prior to joining Synopsys, Morten was a Principal System Designer at ST Ericsson and Ericsson, designing mobile phone and modem chipsets for 19 years. Morten holds 6 international patents for other USB inventions and holds a Master of Science degree from the Norwegian Institute of Technology, 1983. And joining him is Gervais Fong. Gervais is a Senior Product Manager for Mixed Signal PHY IP at Synopsys. Gervais has over 15 years of experience holding product marketing and product management positions covering ASIC, FPGA, EDA, and IP products. Gervais holds a Bachelor of Science degree in Electrical Engineering and Computer Science from the University of California, Berkeley. Welcome, Morten and Gervais. I'll now hand it over to Gervais to begin today's presentation. Gervais?
Thank you very much, Chris, for the introduction, and welcome, everyone. Thank you for attending today's webinar on designing SoCs for USB Type-C products. We'll move on to the agenda, what we're going to cover today. First is an overview of the USB standard's latest version, which is called Type-C. We'll get into the details of what Type-C is, the functionality of all that, and basically what the standard defines. And then more importantly, from a design perspective, how you can implement Type-C in existing products that you might have, as well as future new SoC designs which you want to make Type-C capable. And we'll finish up today's webinar with a Q&A and summary. So what's new in USB? Well, we're going to introduce the new Type-C connector. And with that, you just think by the name, is it just a connector? So Morten, isn't Type-C just another USB connector standard like the A connector, B connector, micro A, B connector, etc.? Or is it something more than that?
Oh yeah, it's a lot more than that. It's not just a hardware change, it's a new symmetrical connector and cable. It's reversible. You can insert it either way. It doesn't have an orientation. It doesn't have a direction. You can use the same connector for hosts, hubs, and devices. It's small. It's robust. It's got improved EMI RFI performance compared to the other connectors. It's expandable. With the 24 pins that are used for power, high-speed and SuperSpeed USB configuration signals, sideband signals. You support 10G, USB 3.1, the new power delivery specification, audio multiplexing. There is something called a debug accessory, which is not yet finished, but it's in there. And you've got alternate modes and all. It's basically expandable. And if you look at the Type-C announcement, which was full of quotes from industry titans saying it's a pathway for future innovation, next generation industry standard, important milestone, important breakthrough, etc. The thing that caught people's imagination and got most of the publicity was the simplified user experience.
So really, Morten, the new Type-C connector, it adds a lot of functionality while still improving the user experience, and that's what people really care about.
Oh yeah, indeed, the user experience is just great. It's small. You can see it compared with the Lightning connector, which was probably the first flippable connector that got public use. It looks a lot larger than the Lightning connector, but the actual receptacle in the product is about the same for the Lightning, the Type-C, and micro AB. And the mechanical conversion from a micro AB product to Type-C is actually very simple. And when you play around and try to plug in the Type-C, it just feels good. But the reason why it's a bit larger than the Lightning is that the plastic overmold and everything, it's more mechanically robust, which means it will withstand the daily misuse that these kind of cables get.
So Morten, let's give everyone an overview of the basics of the Type-C standard. Let's talk about like the electrical and mechanical requirements that are spec'd out in the standard, and talk about the functionality.
Sure. So with standard USB, the standard A and the standard B and the micro A and micro Bs and micro ABs, they are polarized. So there is only one way to plug it in. So when you connect two devices, you've got 4 ways to connect. And only one will work, as I've illustrated here. And let's instead look at Type-C. So Type-C, as we said, is both flippable and reversible. It's orientation pragmatic. It uses full duplication or almost full duplication with both x-axis and y-axis symmetry. If you look at this pinout, you will see that you have the grounds and the V-bus properly symmetrical. You'll have D plus, D minus, and the transmit. Let's look at how this happens. You can see the symmetry on the connector, and we do a 180-degree rotation or an upside down flip. You can see it still matches. You can try that animation again. It actually didn't happen the way it should. Okay, now it's moving here. So you can see the symmetry, and you can see the symmetry when you rotate it.
Well, this is great, Morten. So, future Type-C capable products, you don't have to worry about, which orientation you have to put the connector into and which end of the cable, right?
Correct. Users will love this. That's for sure.
So it's easy for the user to use Type-C. What about our audience today? These are the designers of these future Type-C capable products. What do they have to worry about in terms of making these cables and connectors so easy to use from a user perspective?
Yep. The key to Type-C is actually that it's got dual or duplicated power control and data paths. And making a Type-C product is more complicated due to this. You can see on this drawing from the specification that there are actually 4 possible channels through the cable, depending on the orientation of each end of the cable. So that's true for the SuperSpeed signals at the top. It's true for the high-speed signals in the middle, and it's true for the configuration and control signals down at the bottom of this figure. And of course, for V-bus and ground, there are also 4 possible, but if you connect them together, you just get more current capability. So that's the easy part. So let's look at the dual power control and data paths in a bit more detail again. You can see on this diagram, we've shown a Type-C 5 with 2 possible ports, and the cable connects either straight, crossed one way or the other, or opposite, or upside down on both sides, and it all works. This also works if you're using an adapter. So you have a type A or a type B PHY. As long as you get it correct on the type A or type B side, you can still flip it on the type C side. So this is, it just feels right to do it this way. Of course, since the cable doesn't have a direction anymore, we need to signal what's the host and what's the device. And that was, of course, the advantage of legacy USB. The receptacle uniquely defined it. Now it's the product that needs to define whether it's host or device. With standard USB, if it fits, it works. With Type C, you have to make sure it works. So on the host side, there is a pull-up resistor to signal what's called in the specification a downstream facing port, and the device has a pull down to signal an upstream facing port. The way it works is that the host will monitor if a device is connected, it's being pulled up itself, and then connect the pull down, and the pull down is stronger, and that's how the host knows that the device is connected. Additionally, there is only one wire for configuration, which means that only one of the pull downs will be able to pull down the pull up on the host, and that's how you can detect the orientation, because depending on which way you insert the plug in the receptacle, CC1 or CC2 as they called in the pins, will be activated. So it's simple, makes a lot of sense to do it like this. It gives you everything on those two lines. However, we need to take a reality check, because building a Type C product, the mechanical specification, that's it, that's easy. However, you have all of this. Yep.
So Morten, it seems pretty straightforward to determine, host versus device versus detecting the connector orientation. You show here some things, maybe a little bit under the water. It's kind of an interesting analogy. Looks like there's more to Type C than just what you've just presented so far.
Yeah, it was the best analogy I could come up with. Basically, there is a lot more to it. Not every product needs to think about everything here, but there is a lot under the water that you need to be aware of. That's for sure.
So these are all the different types of potential features that our audience may need to consider as designers of future Type C products then.
Correct.
Be able to take these into account and determine which are appropriate for their products and what they have to design for versus just a simple reversible and non-orientation specific cable.
Indeed, and if we had all day, we could probably cover a lot of this, but we don't, so we have to focus a bit. So we will look at implementing Type C and some simple devices. So basically, implementing Type C, it ranges from trivial to complex, multiple options, and very specific options.
What are some of the different configurations that our audience needs to understand, and what are some of the options that they can choose to introduce Type C products quickly into the market, as well as maybe a little bit more medium term to longer term?
Yeah, let's look at some examples. Maybe that will make it a lot clearer for the audience. And I hope it didn't scare them too much with the iceberg analogy. So let's look at a simple USB 2.0 device first. The mechanical conversion which means fitting a Type C connector instead of a micro B. That's easy. And we've actually done that on a couple of products. And yeah, that's simple. And the rest, the electrical, is actually quite simple too. You need to route your high-speed data plus data minus lines to the receptacle and duplicate them on the pins that are called A6, B6, and A7, B7. You need to minimize the stubs, and there is a single data path in the cable, so only one of these two signal of the four possible wiring maps will be used. Then you need to add the pull-down resistors, 2 of them. There are some people that have suggested you can short circuit the 2 CC pins on the device side and only use 1 resistor. But if you do that, you end up with a corner case when a full feature cable is used to connect the USB 2.0 device, and it will be detected as an analog audio accessory. So it does cost you 2 resistors to convert the high-speed USB device to Type C. The host will detect the pull-down resistors, and as a device, you don't have to monitor for connection or orientation. You just wait for VBus, which is what the standard device does anyway. VBus, when you receive VBus, that indicates the host is ready, and you go on as normal. So to summarize, no PHY changes, add 2 resistors, and wait for VBus. So that's simple.
So what if I want to implement a product with, say, higher current capability, more than, say, the 500 milliamps that's the standard amount of current available from hosts today?
Oh, yeah, that's a very good question, and it's your survey. Many products need more than 500 milliamp current, which you can get from a standard host. I just read about the new phone with a battery that would last for 2, even 3 days. However, the problem is that it takes more than 12 hours to fully charge it, which means that if you only charge it for 6 hours a day, you still only have 1 hour or one day of battery life on it. So Type C has defined a way to signal that the host or the hub is capable of providing more than standard power. So it can provide up to 3 amps, 1.5 or 3 amps is what can be signaled. The host or USB charger signals using different values of the pull-up resistors what the current capability is, and the device detects what voltage you get compared to just detecting that there is a pull-up. The implementation becomes a bit more difficult because it's no longer just a digital detection. You need some precision comparators or an analog to digital converter. But keep in mind that the PMIC or power management IC in a typical chipset for the kind of products we're talking about already controls the current used for charging, and this detection is easy and very suitable for integration in the PMIC.
So let's move beyond devices. What about if you're implementing Type C capable USB 2.0 host?
Yes, a host is getting more complicated, but it's not impossible. As for the device, you need to route your high-speed data lines to the connector, and you need to add your 2 resistors and pull up this time. Note that the spec actually allows you to use current sources instead of pull-up resistors, and the device can have a voltage clamp instead of a pull-down resistor. These are implementation choices. If you're doing a completely discrete implementation, you definitely want to play around with resistors instead of current sources, but inside a PMIC, maybe a current source is more appropriate. If the host has high current capability, you need to have programmable resistors or current sources, at least if you want to be able to vary the current capability, which you can vary it depending on the actual current capability at the time. For instance, depending on whether you're operating off battery or mains. Then the host needs to detect a device connection. When a device is connected, it must enable VBus. So it needs a VBus switch. And normal hosts, they have VBus enabled all the time. However, you can't do that for Type C because if you connect two hosts together and VBus is enabled all the time, when one of the hosts will win that war between the power supplies. You can also, as a host, but this is optional, not needed for a 2.0 host, you might want to detect an electronically marked cable. And you interrogate the cable, and then you know if you can run higher current. And there are also cables that are accessories, but let's not get into that. The minimum requirements for a Type C host is to add the resistors or current sources, connection detection logic. You need to have a VBus switch, and that's it.
So, Moran, what about Type C support for the USB on-the-go or dual-role device configurations?
Yes. Now it's getting to be a bit more complex. First of all, you need to realize that connecting two hosts together, you don't expect that to work. And connecting two devices together, no, that won't work either. So in Type C, we've got something called a dual role port, which replaces on the go. So first of all, if you're going to do a dual role port, you have to have programmable pull-up or pull-down resistors so that at least you can signal to the other end if you're going to change roles. So you can see in this table that connecting two dual role ports together is of course functional, and connecting a host to a host or device should also be functional, and connecting a device to a host or device should also be functional. So that's fine. The challenge is when you connect the dual role port to a dual role port. The classic dual role device for legacy USB or standard A, standard B is not directly supported because the Type C connector doesn't have an ID pin. So you can't force it to be host, or you can't force it to be device with a connector, which means you need an application specific or context sensitive host device role selection, which is perfectly doable, but it requires you to have a link between the very lowest level of your protocol and the applications. Type C doesn't use the legacy on-the-go protocols, the host negotiation protocol for 2.0 and the role swap protocol from 3.0. Instead, it uses power delivery communication. There are some state machines in the Type C specification that can also be used to do role reversal, and you can do it manually, you can have the user do it, or you can do it automatically depending on context sensitive, but none of these are really mapping directly onto on the go. So it becomes a bit tricky to move or port existing products, on-the-go products, dual role products over to Type-C. So it's not impossible, but you really need to think about the consequences of some of the choices you do.
So Morten, we've covered now the Type-C support for the popular USB 2.0 configurations. What about Type-C support for USB 3.0 or SuperSpeed USB?
Yes, we'll start with something simple, which is a Type-C direct connect device.
What do you mean by direct connect?
Well, it's a Thumbdrive or a dongle or a device with a captive cable. So that basically means the device connects directly to the host. There is no cable to be connected to the device, which means it gets really simple because now there are only two possible data paths through the connector, and you don't have to have dual data paths. You don't have to have dual control logic on your device. So you just wrote the plus the minus to the receptacle, SuperSpeed RxTX, and you can add just one resistor because there is only one CC pin that will ever be used, and you just wait for VBus. So no phi changes, even for a SuperSpeed device, just one resistor and wait for VBus as always. So this is easy. However, when we look at the dual data paths configuration control in general for other SuperSpeed devices, it becomes a bit more complex. So let's revisit this schematic for the SuperSpeed Type-C.
So Morten, I see here you've got two separate SuperSpeed data paths to route, but you only need one high-speed data path, and that high-speed data path is shorted together in the connector. Why is that the case?
Good question, Chauvet, but it's about reflections. The USB signal is terminated by the receiver at the other end of the cable. When you create two possible routes, as you do with D plus, D minus, as shown here, one signal goes to the receiver and is terminated, the other goes into nothing and is reflected back to the transmitter. It's just like when you have an echo on your phone connection. For high-speed USB, the reflection is very short compared to the bit time, so it actually works if it's done properly. However, for SuperSpeed, the reflections are always almost as long as the bit time, and the transmitted signal will just be too distorted for the receiver to make any sense of it. So the connection will fail. So you do need two separate data paths that do not interfere with each other. So in the cable, you've got two SuperSpeed pairs, and you use one or the other. You need a switch to select which of the SuperSpeed pairs to use. If you look at an internal solution, you could have a single phi with internal switch, or you could have two phis. This is what's shown on the left of this diagram as an implementation with internal. If you have an external solution, you could have a USB read driver with the switch built in. Lots of hosts today have read drivers because of the distance from the chipset to the connectors on the back plane of the PC. You can have a Type-C switch, or you can even use a general purpose RF switch. And then you need your CC logic And the amount of CC logic and complexity of the CC logic really depends on the product type.
So Martin, I see one of the options that you're showing here is to implement USB Type-C using discrete external chips.
Correct. External chips, they're great for fast time to market and perhaps only suitable for small quantities, especially when you're not sure of the demand. Will people be able to or willing to pay extra, or will they buy your Type-C product instead of a non-Type-C product? However, so time to market, yes, good, but the considerations that you need to do is power cost, PCB area, size, performance, and the complexity. You can see a typical application here, and there are a number of external chips that you need to put in to make it work.
I see another option you're showing here is to use two existing single-port USB 305s.
Yes. It is the fastest time to market for an integrated solution, and many people just raise their hands in horror and say, no, can't do this. But think of it, integrating two small PHYs instead of a large external switch. If you're making primarily Type-C products with this chipset, it makes a lot of sense. You get very quickly to market. Integrating a switch is actually challenging. Worst case, even if you manage to integrate the switch, your channel loss would increase, and you wouldn't have the eye height and the jitter tolerance needed on the receiver side, so you would need an external repeater anyway. So you didn't get away from the external chip or external circuitry. With two PHYs, you use one or the other depending on which lane needs to be active. You have the same channel loss, eye height, and jitter tolerance as a single PHY. There is a larger area, there is a slightly higher power, but remember you're only using one PHY or the other, so you can power off the one that you're not using. So it's not such a bad solution as it looks, but it's not perfect, I have to admit.
What about implementing Type-C using FPGAs? Could this enable our audience to build a quick prototype, for example?
Not only prototypes, but volume production is possible, at least for certain kind of products, maybe not for Thumbdrives. The advantage of an FPGA implementation, it's flexible. A product firmware update could also include an update of the Type-C FPGA. And remember that depending on your product complexity, you do need some sort of CC logic. The dual PHY only solved the problem of the switch, or the dual data paths. And here we have a second generation external Type-C chip. And you can again see that the flexibility is very important. You have a CPU with reprogrammable flash. You have programmable interconnects and programmable function blocks. So even if the Type-C spec is done, implementing it is not trivial, and having the flexibility of reprogrammability is a very useful feature. And here we have another second generation external switch, this time from a company called e-tron Technology. So all of the what I've shown you so far is freely available on the web. You can search out information on solutions that might be suitable for your product. So let's start to summarize.
So Morten, we've covered some external switch chip options, but what what does the audience have to consider if they want to integrate Type-C into their ASIC and come up with a really optimized implementation?
Yeah, it's all about making the right decisions, Survey. You need to decide how to implement dual data paths and how to integrate or not your CC logic. So the SuperSpeed data path summarized there: external switch mux, on switch, dual PHYs, or an optimized Type-C PHY. The CC logic, you can do an on-chip switch. Sorry, you can do an add-on chip. You can do FPGA. You can update your power management IC. Some, as we saw with the USB 2.0 device, discrete components, a couple of resistors, maybe a voltage comparator if you're doing a host. This will be product specific. Then if we look at the implementation options for power, the first is the VBus and also VCon if you're doing power management communication. That's fairly simple, a discrete FET or switch, or this can be part of the PMIC or part of the power supply solution in your actual product. There are also multiple add-ons with different capabilities depending, and some of them will be usable depending on your product, and some of them will be overkill. There is definitely no one-size-fits-all for Type-C. There are also power delivery controllers available, standalone controllers that will do the power delivery communication that's needed for on-the-go, that's needed for alternate modes, that's needed for doing actual power delivery itself. So the sweet spot with regards to what's the best implementation, that will vary from one product to another.
So Morin, what about an example of what an integrated Type-C implementation looks like? For example, how about a system partition example for, say, a future Type-C enabled cell phone or tablet design?
Yep, good. This example shows a typical architecture, and it's built around a Type-C PHY. So we have a CC function, a PD controller, and a PHY. They're separate. If we go back to the first USB spec, that was low speed, full speed. And then high speed USB was multiplexed onto the same pin and connector. Then came the USB car kit, the USB analog headsets, USB on the go, and USB battery charging. And all used the same connector and the same pins, and the USB PHY had to include everything. With Type-C, all the extra signaling is on the separate CC signals. So this allows a lot more flexible partitioning, and the various building blocks needed for Type-C can be placed in the chipset where implementing them makes the most sense for a given product. That opens up a lot of questions. So do you do it, you put things in the PHY or the PMIC or external chips? Do you have hardware state machines? Do you have software tasks to do this? Do you have a CPU there at all? If you're going to do a product, is it device host? Is it a static dual role port so that it's a device today and a host tomorrow? Or is it dynamic like on the go? And what about software compatibility with the existing host software stacks? Also, the Type-C task that differentiates a Type-C device from a standard device. Do you do it in software or hardware? Power delivery controller, do you put it as an external component, integrated in the PMIC, or maybe in your SoC? And what about the power delivery software? If you are doing power delivery as a provider or a consumer, Does it belong in a dedicated MCU, or do you have your application CPU handle it? Because it's the application CPU that knows which applications are running and what the requirements for power are. So in the PHY, you'll typically have a Type C data path, and you also need to have legacy on the go and battery charging in there, because Type C conversion won't happen overnight. There will be a need for adapter cables. You will need to connect to legacy systems. There will be a PD controller and the CC function where you have your switchable resistors, cable detect, orientation detect, the high current capability signaling and detection, and your VBus, dual role port state machines, and the power delivery PHY. All of this can go really anywhere, and it really depends on your system design.
So if you partition your system more in between a processor, a PMIC, and the PHY, what solutions could designers look for when they're implementing an integrated Type-C USB controller and PHY?
I would strongly suggest they look at an optimized Type-C PHY. The advantages over a switch or multiplexer solution is that you'll have an optimized area and power. You'll have a really simple floor plan, easy PCB routing. You can basically route directly from the PHY to the connector. You'll have the eye height, jitter tolerance, and signal quality as a single PHY. You don't need to think about drivers. And you can have a very flexible partitioning. So you can put your precision analog and power in PMIC, state machines. They can be in hardware or software. You can have functionality extensions in software or PMIC hardware, or add external chips. You don't have to change your SoC and the Type-C PHY. So you'll have low risk, and you can reuse your SoC for multiple projects by just adding the required CC functionality and additional Type-C functionality externally to the PHY.
So Morin, thanks for a great overview on the new USB Type-C standard. So if I can summarize it, Type-C is a common connector. It supports all 5 USB speeds from the original USB 1.1 speed all the way up to the latest USB 3.1 10 gig data rate. It's a flippable and reversible standard for the cable. As you've explained, there's enhanced mechanical and EMI and RFI design implemented into the cable itself. And it's also extensible, so it has the ability to deliver data, control, power, as well as analog audio. And there's some additional alternate or guest modes. So, when you look at this really keeps the USB interconnect very relevant for the next 10 or 20 years, for example. And what you're saying here, though, is that implementation on Type-C could be non-trivial. For very simple, say, existing USB 2.0 device implementations, that could be fairly straightforward. But for the more complex examples that you presented today, the cost could be significant, and therefore, if you're going to design to have some of these more complex features, designing the product properly and doing a high-quality job is, I think, really, really important. And one of the things that our audience can look for is an optimized system design for Type-C, because especially if you're doing, for example, USB 3, you basically have to have 2 SuperSpeed data paths you have to contend with, and not just a single SuperSpeed data path in the historical USB 3.0 implementations. I think lastly, Type-C IP will be available be available from Synopsys as well as other providers, and I think that will help allow the industry to get a more integrated, more cost-effective solution into the market more quickly. But for those of you that need to implement Type-C quickly, products are out there today, external discrete solutions, for example, that allows you to kind of get a very fast start on implementing Type-C in your products. So thank you to the audience for listening in on our overview today on USB Type-C. I'll turn it back over to you, Chris, right now to see what types of questions that the audience may have for us.
All right, thank you, Gervais. Great presentation between you and Morton. Just real quickly before we begin with today's Q&A session, I would like you to fill out the feedback form that's opened up on your computer. To complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. And now we'll move on to our question and answer section of the presentation. Just as a reminder here, if you have a question for our presenters, just go ahead and type your question into the text box located below the media player, then click the Submit Question button. And as a reminder, we'll try to get to every question that we can in the time that we have left, but if we don't get to your question today, someone will get back to you via email. So let's go ahead now with our first question. Our first question is, what could be the maximum length of the cable before worrying about the ringing, reflection, and impedance questions? And that's for Morton.
Yeah, that's a good question. However, it's actually not relevant because all the reflections and impedance is on the device side, so the cable doesn't matter. So, and if you do the high-speed routing according to what the connector manufacturer tells you, then you should be fine. There will be a very short stub. But you can't say, oh, I will only support a very short cable, so I can do the so I don't need a dual data path for SuperSpeed. That won't work, unfortunately.
All right, thank you, Morton. Our next question for you: when do you expect the first Type-C products to come on the market?
Yes, they're actually on the market already, being sold out so quickly that the factory can't keep up. The Nokia N1 tablet is the first available product. Other products have been announced, like motherboards with Type-C, even with USB 3.1 10G. And there are consistent rumors about other products that will be launched soon. So, yes, Type-C is happening now.
All right, thank you, Morton. Our next question for you: what is the max power able to be delivered over USB-C? I've heard up to 100 watts, but the presentation today only showed 15.
Correct. The Type-C supports the simple power enhancement, which allows 1.5 or 3 amps at 5 volt. And then if you do power delivery, which means you have to have power delivery communication, you have to have programmable power supplies, etc. You can do 12 volt or 20 volt V-bus instead of 5 volt, and you can do 3 amp and 5 amp, giving you a maximum of 100 watts, just as for the old power delivery specification. But power delivery is then completely separate from USB as such, which is why we didn't cover it. Also, we would run out of time if we started covering power delivery. But you can do with power delivery up to 100 watts.
All right, and our next question for you: what is the maximum cable length on USB 3.1? And then it says 10G question mark.
Yep, good question. The Type-C connector is actually a better connector than the standard A, standard B, but it's really the cable which is the limitation. So it's still 1 meter for 10G operation. However, if there are indications that Type-C can be extended, And if you have a long cable and you use both data lanes sometime in the future and that is standardized, you can have a higher total data rate through a longer cable. But at the moment it's 1 meter for 10G and a defined 2 meter nominal max cable length for 1G or for Gen 1 or 5G operation.
All right, and our next question for you, what products will benefit the most from Type-C?
Well, the obvious answer would be every product, but I think products that people use every day that are small, that have a non-obtrusive receptacle somewhere that you need to plug in every day in all sorts of situations, whether it's sitting in the car or lying in bed remembering to plug in your phone so it will charge overnight. That's where you will really appreciate the flippability of it. Then as for the other functions, I think every product will benefit from having Type-C, even if it doesn't use any of the advanced features of Type-C.
All right, and another question for you. What about backwards compatibility?
Yes, that's a very good question. And the Type-C specification defines a lot of adapter cables that allows you to have backwards compatibility. For instance, if you want to connect a Type-C device to a standard A host, then it's a simple adapter cable. If you want to connect a Type-C host to a standard device, that adapter cable exists, and the adapter cable includes the pull-down resistors that the device would normally have. So as soon as you plug in the cable, the host will enable VBus and wait for a device to do its thing. So backwards compatibility is taken care of using adapter cables, and functionality-wise, everything will be fine. So there is definitely backwards compatibility, just like with any other USB standard that's been introduced in the last almost 20 years.
All right, and we have one more question here. Will customers suffer during the transition period before everything is Type-C?
Depends on the definition of suffer, but no, we don't expect them to. I think they will be so happy with Type-C and the performance and the usability that the only suffering is because the manufacturers aren't quick enough to get Type-C products on the market.
All right, and another question for you. How about Windows drivers and Mac support?
Absolutely no issue, because it's still standard USB. It doesn't necessarily know about the receptacle, whether it's Type-C or standard AB. There is a need in some products for a Type-C task, which can run in software or hardware, that will set the switch to the right position. But that's trivial, and it doesn't affect any of the upper layers, including drivers on Windows or Mac or any other system.
All right, and that looks like about all the time that we have for questions for today. I'd like to thank Morten and Gervais for a great presentation and Q&A session. Just a reminder, if we didn't get to your question, then someone will get back to you via email. And for more information related to today's webinar, please visit any of the resources links open up before you. Within the next 24 to 48 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Additionally, you can view today's event on demand by visiting www.techonline.com. Once again, we'd like to thank you for attending today's webinar, Designing SoCs for USB Type-C Products, brought to you by Synopsys, Tech Online, and broadcast by UBM. This webinar is copyright 2015 by UBM. The presentation materials are owned by or copyrighted, if that is the case, by Synopsys and Tech Online, who are solely responsible for its content. The individual speakers are solely responsible for their content and opinions. On behalf of our guests, Morten Christensen and Gervais Fong and Synopsys, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.